So I would like to mention one thing. In this week's sample questions, I think 22, the TA will do a rather interesting ionic bonding problem. It's an ionic solid. So the problem is as follows. I think you may need to do it in a future homework problem. Let me see here. So I will have a plus minus ion. But they form an array. Okay, this is a 2D version of the problem, but basically in real life you have 3D version. And here's a very interesting non-quantum mechanics problem. So let's say you sit here. You are given the equilibrium separation, right? So you sit here, do you see that there are 4 nearest neighbors of negative ions? You see that? Okay, so that will contribute something like minus E squared over 4 pi epsilon 0. Okay, and I think it is like square root 2. No. It's 1 over square root 2 R0. And then I will have 4 of them. Okay, so do you understand what I'm trying to write down? This is the energy, Coulomb attractive energy. If you sit here and ask what these 4 neighbors do to you, do you understand? You follow up to here, and then you will see there are 1, 2, 3, 4 so-called next nearest neighbors. Okay, but the sign will be different. This is attractive, but then the second term will be minus something. Okay, then you go further, you will meet some negative neighbors again. So here, I think here, same distance. Okay, then you will have a plus term. Then go further, you will have the plus neighbors, then you have a minus term, and so on. The question is, now these are all numbers. But with alternating sign. I mean plus minus alternating term by term. The question is whether this thing can be summed up. If it can, what is the number? Okay, so the TA this week, tonight, this evening, will do a, I think it's sodium chloride for you, okay? And that is a very famous solid state physics problem, chapter 1 in solid state physics about crystal structure. You will see that if you want to sum this to convergence, you need to write a program because you need many terms in order to get at the convergence. The bad thing is it is alternate signs. So this is an advertisement of the sample questions. So now we get into the heart, a very important part of our discussion of molecules. So pay attention. I try to minimize the mathematics here, but the content is quite quantum mechanical. So the first thing I would like you to realize or appreciate is that for any molecules, the quantum mechanical Schrödinger problem is very difficult to solve. And then next step, you can better appreciate what nature offers us. We can make good approximation to make sense of the existence of molecules. So the first thing is simplest molecules problem cannot be solved exactly. Then I would like you to appreciate the beauty of developing approximations applied, street fighting quantum mechanics. So now again, we would like to consider an abstract diatomic, so AB molecules. At the end, we will do something even simpler, homonuclei. So it is a ACE2, okay? That makes life even easier. But for the moment, we just AB could be in general different atoms. So to make connections to what you are learning in your thermal and statistical physics, so let's consider we have a jar, a cylinder, full of a gas of molecules. Have you done ideal gas? Do you know this thing? 3nkt divided by 2 is the internal energy. Do you know this? You have that? Okay, good. Now, so I would like you to make connections. Okay, so now you have a jar of molecular gas. Inside this gas, the molecule is AB type. So there's this thing. So now you are here, you look at this thing. If you zoom into one molecule, then the situation is like this. You have an AB nuclei. The shaded part is the electronic wave function, how the electrons distribute. We need to write down as an equation that governs how the electron distribute, the Schrödinger equation. And it is the electrons distribution that is responsible for forming the bonds. That is to say, the electrons, the wave function at the end will need to nuclear separation, the energy between the nuclei, a curve like this. This will be due to electron distribution. Okay, this is what we are going to get. And then if you zoom in further, once you have this bonding form, it could be represented rather accurately near the bottom of the potential energy. Is like quadratic parabola. Therefore, it's like a spring. And then two things could happen. It would vibrate. And then AB with a bond is like a rod. If you do, this is already taken care of the vibration. You decouple the vibration with the rotation. The rotation part is like two balls, A and B balls with a rod representing the bond. This thing can rotate. Okay, so it can rotate. A top wheel will rotate. Okay, so that will be rotational motion. That will be vibrational motion. But then there is a center of mass here. The center of mass is freely moving, and this center of mass freely moving will contribute this 3/2 NKT to the internal energy of the gas. Connected? You understand? Okay. So in our course, we will not worry about the translational motion of the center of mass. We will transform to the center of mass coordinate and try to understand how the electrons want to distribute themselves. What is the preferred separation? What is the vibration about the preferred separation? And what is the rotation allowed for the molecule? So this is our focus. The center of mass motion is related to what you learned in your thermal physics course. Okay, so this is what I just said. In quantum mechanics in our course, we don't worry about the center of mass motion, it's freely moving anyway. Then we focus on the relative motion. And then we will have a quantum mechanical problem. You put it at a certain separation. How will the electrons respond? And how would the electrons select a preferred separation, the vibrational motion, and the rotational motion? So this is our duty. This is Professor Gore's duty. Okay, and in fact, okay, now, so you know this part, right? And then do you know the heat capacity, right? The heat capacity is 3/2 NK. Oh, 有冇學過呢個? Have you learned this? It is 3/2 R per mole. Have you learned this? 有冇? 有啊? Okay, now. So let's make further connection. So you have learned this. This is due to translational motion. This is the center of mass motion. Okay, and then the heat capacity will be du dt. Okay, if you want per mole, then it is something like this. Okay, so this thing is a constant, so it's something like here. And usually for gas at room temperature, so you are here, right? Something like that, right? So this is, okay. Now, I just want you to know, maybe in your thermal physics course later on, you will see the heat capacity curve actually has some more steps. Okay, and this part is due to the rotation. Rotational motion, it is exactly what we mentioned, okay? And this part is due to vibration. Okay, so for diatomic gas, the heat capacity is not just a flat 1.5 R. Depending on the temperature, you may excite rotational contribution as well as vibrational contribution. But the translational one is easiest to excite. That's why you always see that part, all right? So keep this in mind. Our course is not disjoint from the other course that you are learning. Physics is physics. It doesn't matter which course you learn. So let's continue. The next part, I would like to write down a scattering Hamiltonian for the AB molecule and convince you that nice thing is we know the governing physics, Schrödinger equation. The bad news is we can't solve it, okay? So let's sit down to work. So I have an AB molecule. The setup is that I have a nucleus A, mass MA. Nucleus B, mass MB, all right? Now, atom A has plus ZA charge. So in the periodic table, it is the ZA element. Count, maybe 11, and then it is sodium, okay? Then it has ZB plus charge in the nucleus. Atoms are neutral, therefore, altogether there are ZA plus ZB electrons. The whole thing is neutral. Okay, so everybody, do you follow me? I'm setting up. This is an important part. Okay, so you see the whole quantum mechanics problem has many particles in it. How many? ZA electrons, ZB electrons, and 2 nuclei. So it is N plus 2 body. If I call N is the number of electrons, ZA plus ZB. So now you see, it is even worse than the atomic problem, right? Then we want to write down the Hamiltonian. So before we write it down, let's think. I have nuclear number 1, therefore it has a kinetic energy. Number 2, so it has a kinetic energy. We will have kinetic energy terms of the nuclei. We have that number of electrons, so there are that many number of kinetic energy terms for electrons. How about the potential energy terms? Okay, T plus V, okay, Hamiltonians. So we have each electron will see nuclear A. Each electron will see nuclear B, right? Now there are electron-electron Coulomb repulsion. Many terms. At the end, we also have this nucleus seeing this nucleus, the nuclear-nucleus repulsion. So guys, do you understand? We have that many terms to write down in the Hamiltonian. Amen. Get that? Once you have this list, is to execute it out, right? So I try to write it as clear as possible with 2 colors. The black one are electrons stuff. The blue ones are the nucleus stuff, all right? Now, term number 1, kinetic energy of the 2 nuclei. So do you understand this? P squared over 2m, but it is referring to nuclei. I use a capital. So this is the kinetic energy in classical mechanics for nucleus number 1, A, nucleus A. Get me? Turning it into operator, I will have a Laplacian referring to the coordinate here for nuclear A. Get me? Then I will have kinetic energies of all the electrons. So for 1 electron, it is this kinetic energy term. The small m is the mass of electron. Let me emphasize one more time. This is smaller, much smaller. Any one of this will be thousands of times or 10,000 times bigger than this mass, okay? Now I need to sum up all the electrons. How many of them? N of them given by ZA plus ZB. Follow this? Come back. Then let's go down the list. There's a nucleus repulsion term. Sorry. So I want to write that down first. In blue, the nuclear term. So I have a nucleus at RA, another at RB. The separation is this. They are both positive charge. Therefore, it's a plus Coulomb potential energy, Coulomb repulsive. So that is the total charge. So this is the nucleus repulsion. Now, every electron sees nuclear A. So every electron has minus E. Nucleus A has plus ZAE. Therefore, I have minus ZAE squared. Electron number I is at small ri. The separation from the electron to nuclear A is this Ri minus capital Ra. All right. So this is Coulomb attractive minus I. All right. This is all electron sees nucleus A. This is all electron sees nucleus B. Okay. And the last term is electron sees each other. So pairwise, they will have a repulsive plus E squared over their separation Ri minus Rj. I have to sum up all pairs. Okay, pairs means I don't double count. 1 with 2, 1 with 3, 1 with 4. But when I start with 2, I don't count 2 with 1 again. Pairwise, only once. Now I would like to ask everybody here, do you understand this is the Hamiltonian for my diatomic molecules? Have any questions? Okay. Now, the point is that we know the governing equation. H psi equals E psi. We are done. Go home, right? A month and a half later. Okay, come back for the final exam. That's it, right? This is the governing equation. You explore the consequences. Okay, so there's a question about what happens if it is triatomic, 1 A, B, C. Okay, now think about that. You will have 3 nuclear motion term, 3 kinetic energy. You will have many electrons thing. All right, then you will have ACSB at the nucleus AB and BC and AC. You will have 3 terms. Follow me? Repulsive, all electrons sees ABC nuclei, or right? And then you will have Coulomb repulsion that can be written down. Is that okay? More terms, more complicated. Okay? Get me? Now, therefore, it is not about we don't know the equation or we don't know the physics. We know the physics. Schrödinger equation. That's it. Done. Okay? However, it's so scary. How could we handle it? Okay? That comes the next point I stress at the outset. I really want you to appreciate the beauty of developing powerful approximations. In order to start with this thing, at the end, we understand a lot of molecular physics. And even we can compare our understanding with experimental data, with molecular spectrum. So first thing first, I would like you to realize the following thing. This is a quantum mechanical operator. You see, in principle, these are momentum operators, p squares, and these are position operator, but in the position representation is just the position, okay? And then this is the position operator of electron. This is the position operator of nucleus. Now, the point is, you see all this kind of coupled form. Therefore, it is hopeless to separate the electron problem with the nuclear problem. Okay, what I'm saying is that this Hamiltonian, you cannot, in principle, we cannot use separation of variable, separate the electron coordinates and the nucleus coordinates. Okay, so it may be clearer on this page. Here is very formal. The Hamiltonian, in principle, is a function of momenta and positions or coordinates. Now, not only we have the momenta of electrons and positions of electrons, the Hamiltonian also dependent on the two momenta of nuclei and position of the two nuclei. So this is our variables in the molecular Hamiltonian. Okay, in shorthand notation, I just write it like this. What is the governing equation? We want to solve for the allowed energies of the molecules. Therefore, no problem. Take what we wrote down, multiply by something. It is a molecular total wave function. In principle, in the position representation, it is all the coordinates, including not only the electron coordinates, but also the nuclei coordinates. So it is a function of these variables. So I have H psi equals, and this is the thing we want to solve, the allowed molecular energy. What are the values of the energy that a molecule can take on, right? So this is the, just like atomic physics, you have H atom, psi equals the energy allowed for the atom psi. But we have nuclear coordinates now, okay? So you see, this is the governing equation, and we know that, all right? And we want to solve this at the end, okay? So take this in mind. At the end, we will write down, well, after 40 pages, we will write down an approximate expression for this molecular energies. That will include the electrons contribution, the rotational contribution, and the vibrational contribution. So at this point, let me summarize. AB diatomic molecules. We know the Hamiltonian. Take this H psi molecule total equals what we want to get, allow the energies of the molecule times the molecular wave function. Okay? Now, can we solve it? The answer is no. I already mentioned that because you know these are coupled. Separation of variables cannot work in principle. Then some of you may think, I can take one variable out by defining the center of mass. Very good. So you know classical mechanics. And that will be the translational motion that we talked about. Very nice. Therefore, let's do it and see whether that will help us a little bit. Therefore, the nuclear motion MA and MB, we defined a 1 over mu equals 1 over MA plus 1 over MB. A remark here is that in making this approximation, we take this MA and MB to be much bigger than the electron mass. Therefore, we ignore the electron mass in defining the center of mass. The center of mass. They are not important, that is to say. And then the relative motion of the nuclei will be RB minus RA. I will give you a figure, what this RA, R mean, and R and the capital R. Capital R is a vector pointing from A towards B, okay? So this is R, okay? Go to the B side, okay? So good. After you do that in classical mechanics, you know what happened, right? There's a center of mass that is freely moving. That is the translational motion in the cylinder. And after that, you have a relative motion. It looks like you sit on this one, and you look at the other one that is moving relative to you. And this separation is R. Okay, this thing. Good. You take out one coordinate, but the bad news is that you still have n electrons plus one relative motion for diatomic problem. So this is the figure defining everything. For the previous one, this one, I am taking an arbitrary origin, let's say here, okay? Then I will have RA, RB, and so on. But now after you do the center of mass, if you sit on the center of mass, then the relative motion remaining RB minus RA is this one. Okay, so this is R. Okay, so keep this in mind. Later on, we will see this R comes in again. And the R without the vector sign is the distance between the separation between A and B. And now, an electron, anyone say this one here, when it sees A, okay, what is the separation? This is R1 minus RA. That's right, okay? And then the separation between these two electrons will be R1 minus R3. Okay, so now it is the symbols after you make the transformation to the center of mass. You take out one. Does it help? Well, it looks a little bit shorter. So let's say, so now the nuclear motion, I don't have two terms anymore. I only have the relative motion using the mu, the reduced mass, has to do with nuclear masses. Okay, then all the electrons, nuclear repulsion, now the separation is given by this capital R. All the electrons sees A, all the electrons sees B, it is attractive. and the electrons repel each other in pairs. Okay, so there's a lot of term here. In principle, it is n times n minus 1 over 2 terms when you have n electrons, because there's that number of pairs. Okay. And then the Schrödinger equation becomes H total, the total molecular wave function, which is, we have one less variable, nice, but still you have this relative distance, relative displacement of the two nuclei inside the wave function, equals what we want to solve times the energy. Okay. The difference between this energy and the previous one is that there will be no center of mass freely moving kinetic energy inside this eigenvalue. We already singled that out and we don't consider that. It's too simple. It's freely moving. Okay. So now the difficulty I already mentioned is that we have nuclear operator, this is momentum square position together with electron momentum and electron positions, all in one Hamiltonian. Therefore, we cannot separate the terms into nuclear operators only plus electron operators only. If we can do that, then separation of variables will work. But inspecting this, we know that separation of variables in principle does not work. So this is the statement. This is what we want to find. If separation of variable works, then we can write the total molecular wave function as a product. A wave function of the electrons that has to do with the electron coordinates only, and then another part that has to do with the nuclear relative motion only, related to the relative position, displacement R only. Okay, now this is true if separation of variable works, but it is not true formally here. Okay, so I pause here. Do you understand this statement? You get that? Okay. Now, the art and the science of doing applied quantum mechanics is that when you realize there's something you want to do, but cannot be done formally, the idea is, why not try it out and see whether it is already a very good approximation or it is lousy. You have to try it, right? So that is the approximation that we want to make. We really want to do it. Although formally we cannot do it, but we really want to do it. So that is an approximation that we want to make. Behind this is a big, famous approximation called the Born-Oppenheimer approximation, after two big names, Max Born and Robert Oppenheimer. Oppenheimer was the head of the Manhattan Project that makes the first two nuclear bombs during the Second World War. But he did quantum mechanics, the first generation. So the next step is we will try to make this approximation and justifies what has been approximated. Okay. So we would like to do that. Now, this part with electron coordinates only would mean how the electrons distribute according to, say, try to lower the energy. Okay, how would it distribute when the nucleus are fixed at a certain separation? After the nuclear is fixed, it is just a number. It is no longer an operator. It becomes a parameter. A parameter is just a number, okay? And then after we know how the electron distribute for different fixed R, there will be a minimum in the curve, in the energy, and that will define the bond length, and then this part will take care of the vibration about the equilibrium position and the rotation like two balls with a rod. And that is the big picture. So this is the Born-Oppenheimer approximation. We want to make this approximation anyway. We want to ask, is it good? Okay, what are we doing behind the scene? Okay, will this come out? And what is this nuclear part related to vibrational and rotational motion? Now, this is easy, but you need to review for yourself oscillator physics and rigid rotator or rotor physics. So let me introduce the key idea. I mentioned it at the outset. The key idea is that electron is very light in mass compared with any nuclear mass. Usually it's off by 10 to the 5 power, 10,000 times. Therefore, we will expect nuclear motion is very slow. Electron motion will be very fast. So you can think about the real situation is as follows. The nuclear is vibrating, but you can't hardly see it, okay? And then for the electrons concerned, it is rapidly moving. Think about something like Bohr model, it's an orbit, okay? So it's like you are running on a 400-meter track, but the track is slightly shrinking, some slightly extending in a matter of days. So you don't see that. After you go through a round, you see, oh, haven't changed. Another round, haven't changed. Another round, haven't changed. It's basically this kind of picture proposed by Max Born. Okay, and then to move forward. So let me flash you the idea, and then I will continue on next time. So that will give us the following idea to work with. Let me fix the separation at a certain value. I don't know which value is the good one. I tried different values. This value. Then I solve the electrons Hamiltonian. Okay, I fixed the separation. So this is an electron problem like an atom. Therefore, for one particular separation, I will have several or many, infinite many electron energies. Then I try another separation. I will again have many solutions for the electron distribution. And these are the allowed energies, electronic. I try another one, I will have another set of values. I try another one, I will have another set of values. So here in this picture, I illustrate 3 different arbitrary set separations. Look at the lower one. Okay, it started to emerge. There is a curve. If I try very many separations. So at the end, you will see I join the curve and there is a minimum. And that is the best separation. Electrons want this particular separation. Electron sets the bond length. And that is the electron part of Born-Oppenheimer approximation. Last statement. Then the nuclear part will come in again. Because there's a minimum, the nuclear will oscillate about this minimum, and also the whole molecule with this equilibrium separation will rotate. These 2 parts together with the minimum energy, the electron energy here, will be our total energy of the molecule. Okay, where's my Schrödinger equation? Okay, so this is the journey that we will go through on Thursday in the Born-Oppenheimer approximation. At that point, chemistry becomes part of quantum physics. And frankly, quantum mechanics and quantum mechanics only is the theory of bonding, most of the chemistry. Okay, so I will stop here today. If you have questions, please ask.